Welcome to lecture number 14 for ECE 341, Random Processes. In this lecture, we're going to look at the uniform distribution. Now, a continuous uniform distribution is a PDF where the probability is the same over the same range. So, for example, a uniform distribution over the range of 0 to 1 would look something like this. It has an area of 1, a width of 1, therefore the height has to be 1. The CDF would be the integral of the PDF, is the area to the left of x. So currently the area is 0, and then it goes up to 1 at 1. That's the CDF. A couple examples of a uniform distribution. Resistors. For example, if you buy a 1K resistor, it'll have a tolerance. If the tolerance is 5%, that means that it'll have values somewhere between 1K minus 5% and 1K plus 5%, between 950 and 1050 ohms. Now, what it is, I don't really know, so one way to model that is a uniform distribution. You can assume any values between 950 and 1050 plus minus 5%. If you look at the data sheets for a transistor, like a 3904, there the data sheet says the gain is somewhere between 100 and 300. I don't know what the gain is going to be, so what I could do is model that as a uniform distribution. I could take any value between 100 and 300 ohms. If it does that, it meets the specs. A MOSFET. A MOSFET is a voltage-controlled resistor. There is a gate voltage that turns on the MOSFET, makes it conduct. The gate voltage oftentimes vary. So again, if you take the data sheets, like an IRF 941 MOSFET, the turn-on voltage is somewhere between 2 volts and 4 volts. I could model that with a uniform distribution. Anything between 2 and 4 would meet the specs. So that's examples of where you'd apply a uniform distribution. Now, some properties of uniform distribution. If I have a uniform distribution between A and B, the height has to be whatever it takes to make the area 1. The width is B minus A, therefore the height has to be 1 over B minus A. That's to make it a valid PDF. The mean is the center of mass. Kind of tell that the center of mass is going to be just by symmetry right in the middle. That's B plus A over 2. The variance is how far is each point from the mean squared times probability. The probability is fixed. If you integrate this out, I wind up with B minus A squared over 12. That's the variance. And the Laplace transform, also known as the moment generating function, is take the derivative. I get a delta function here, negative delta. So that's the height is 1 over B minus A, integrate once, 1 over S, delta divided by A minus delta divided by B. So there's the Laplace transform, or moment generating function, of a uniform distribution. So not a whole lot you can do with uniform distributions. That's kind of all there is to it. If I start combining them, that's when it gets kind of interesting. Suppose I have two uniform distributions and I want to find out what's the PDF of the sum of A plus B. Now there's a couple ways of doing that. I could convolve their PDFs or multiply their moment generating functions. Either way works. So just for fun, let's start with the uniform distribution between 0 and 1. Convolve it with the uniform distribution between 0 and 1. What is the PDF of A plus B? Now, one approach is to use convolution. With convolution, that'll be the integral of A of t times b of x minus t dt. So here's kind of what convolution looks like. I'll take A of t, that's my uniform distribution between 0 and 1. Convolve it with b of x minus t. So this is sweeping over t. So I take minus t, I flip it to get this guy, and then I sweep. I'm going to sweep from x, say when x equals 0, I'll be right here. As x increases, this slides to the right. So this is kind of what that looks like. I'm going to use MATLAB to try to simulate convolution. So if A is a uniform distribution between 0 and 1. B is the uniform distribution between 0 and 1. This is A of t. This is B of t minus tau. C is the product of the two, and let's sweep them as time goes on. So here's what's happening. Here's my B is sweeping to the right. The right endpoint is t. The part in blue is the product of A times B. The part in red is the integral, the total area under the curve. So what you kind of see as I sweep right, I start with an area of 0. I catch more and more area. Eventually the area goes to 1. Then as I leave, the area goes back down to 0 and it remains 0. Let's run that again. Let me make that a little bit bigger so you can see it. So here's the convolution. I take B, sweep it right. This is t equals 0. The blue area is the common area. Take the area of the blue area. As I sweep right, I catch the end, then it goes back down. That is the convolution of two uniform distributions. And to kind of illustrate what that looks like, let's try two other uniform distributions. This would be a uniform distribution with the width of 2, between 0 and 2, and a width of 3, goes between 0 and 3. So when I do that, here's the uniform distribution width of 2. The light blue one is the width of 3. I sweep it right. The dark blue is the product of the two. Area increases up until I get to this point. Then I reach the maximum. Area starts to decrease. And then goes to 0. If I delay 1, say this is between 1 and 3, here's what the convolution looks like. So again, A is now between 1 and 3. I'll sweep B left from the left. When I hit it, I start to include area. That's the dark blue area. Area starts to increase. That stays a constant. Area starts to decrease. So there, the red line is the convolution of A and B. That's kind of one way to do convolution. So graphically, what's going to happen is I start out with an area of 0. As I sweep B to the right, I start to hit A, picking up area. Area increases up until I get to 1. Then the left end starts pulling away. Area goes back down to 0. So that's the PDF of A plus B. I can follow the two PDFs. I could solve that using calculus. Now this is kind of painful. I take the PDF for a unit step. That's u of t minus 1. The PDF of the unit step using x of x minus t. Integrate over t. Now do all the products. I've got 4 different product terms. Here's u times u of x minus t, u times u of x minus t minus 1, all sweeping from minus infinity to plus infinity. Here, this u of t turns on at 0, so I can replace the left endpoint with 0. This turns off when t is bigger than x, so this is 1, stopping at x, the integral of 1 between 0 and x. This guy is, we'll bring the minus sign outside, 0 for t less than 0, that's at this point, 0 for t greater than x minus 1, so it's the right endpoint of 1. Likewise for these terms. Now the integral of 1 between 0 and x is just x, providing x is bigger than 0. Integral between 0 and x minus 1 is x minus 1, providing that x minus 1 is bigger than 0. Integral of 1 between 1 and x is x minus 1, providing x is bigger than 1. An integral of 1 between 1 and x minus 1 is x minus 1 minus 1, x minus 2, providing x is bigger than 2. Simplify, you get this function. That was kind of painful, but I could convolve these using calculus. That's one way to do it. I could convolve them using moment-generating functions. This is actually much easier. The Laplace transform of a step is 1 over s times 1 minus e to the minus s. Here's the unit step. When I convolve in time, I multiply in Laplace. So multiply these two together. So y of s is just a times b is the product of these two. So we get 1 times 1, well, 1 over s times 1 over s, 1 over s squared. 1 times 1, e to the minus s plus e to the minus s is e2. And e to the minus s times e to the minus s is e to the minus 2s. Take the inverse Laplace transform. 1 over s squared is t. Delayed by 2 seconds. This is minus 2t. Delayed by 1 second. This is t, or x. So that's the inverse Laplace transform. That's the PDF. Which is, take this guy, this is just t u of t, that's a ramp. At 1, this kicks in, minus 2t, starting at 1. So this is t minus 2t, comes back down. Then at 2, I kick in and add another t. Gives you this. There's your triangle. I could solve in MATLAB, and that's kind of what I did in the simulation. I'm going to sweep from 0 to 2. Well, here's a hard way to do it. This is the hard way to do it. Kind of fun to watch. You're sweeping it, watching it go forward. That's doing the convolution the hard way. MATLAB has a built-in function for convolution. That's the convolve function. So this would be for those two functions. If I go back to the one that we're looking at, unit step between 0 and 1. Again, here's the hard way to do it. Here's the convolution, so you kind of see what's happening. I sweep b to the right, multiply the two together, take the area under the curve. The red line is the answer. That's the convolution. That's the long, painful way to do it. An easier way, by MATLAB, so your sampling rate, your dt is 0.01. T goes from 0 dt to 2. A is 1 times t greater than 0. I'll tell you what. Perturb it by epsilon, so you don't have to worry about equals. A is 1 times t less than 1. B is 1 times t less than 1. C is the convolution of A and B. Now when I do convolution, that is the summation. To make that integration, I need to multiply by dt. So if I plot, convolution, you get twice as long. here's what I get. So A and B are unit steps. The convolution is your triangle. So I can use convolution just as well. Convolution actually is pretty easy with MATLAB, kind of painful by hand, really easy with MATLAB. Okay, so that's the convolution of two uniform distributions. That's also equal to, in MATLAB, let's say A is rand, B is rand, C is A plus B. This is the PDF of C. When I do that, most of the time I'll be right around 1. I could get a number up to 2, could get a number close to 0, but not very likely. So doing a whole bunch of these, kind of see the answer is always between 0 and 2, kind of close to 1. That is the sum of two uniform distributions. Now what that corresponds to is two resistors in series. But model a resistor as being a uniform distribution between 95% and 105% of the nominal value. What I'm really doing is I'm convolving two uniform distributions. I have two resistors in series. What the PDF looks like is that. Suppose I have three resistors in series. Find the PDF. Well, again, I'm not going to do that. Well, kind of a painful way to do it. I'm not going to do that by hand. I'm not going to use generating functions. I'm going to use the convolve function in MATLAB. A whole lot easier. What I could do is suppose I have three uniform distributions between 0 and 1, A, B, and C. To find the sum of the three, I'll use convolution. When I convolve in continuous time, I need to integrate, so multiply by the step size. That gives you A and B. Take that result, combine it with C, I get A, B, and C. Put it all together, that's what the PDF looks like. You kind of see that in MATLAB. Sum three uniform distributions, it looks like this. Answers are always between 0 and 3. They cluster close to 1.5. That's kind of what I'm seeing. Occasionally, I might get a really small number close to 0. Occasionally, I might get a number really big, close to 3. But usually it's right around, between 1 and 2. Found using convolution. Suppose I have 32 resistors in series. What does the PDF look like? Well, that's the same problem of adding 32 uniform distributions. I can do that using convolution in MATLAB. Here is a uniform distribution. Here's two uniform distributions, 4, 8, 16, 32. Plot it. That's what the PDF looks like. This is a bell-shaped curve. That's the central limit theorem one more time. Keep on seeing that bell-shaped curve. In fact, that actually happened after 3 uniform distributions. With 32, it really looks like a bell-shaped curve. We'll be talking about the normal distribution later. It keeps on occurring over and over again. Probably the most important distribution in all statistics. Now, where uniform distributions are used, well, one place they're used is analyzing circuits. So suppose I had a circuit with a bunch of resistors in it, and each one had a tolerance. What is the PDF of the resulting circuit? For example, if I have one resistor in series, two in parallel, this is 100 ohms, 200 ohms, 300 ohms, what is the PDF of the total resistance? Well, if they are in series, they add. I know how to add uniform distributions. In parallel, it's the sum of the inverses inverted. How do you combine uniform distributions when it's the sum of the inverses inverted? Actually, I don't know. This is where Monte Carlo comes in. I can run a Monte Carlo simulation for this pretty easily. So, let's use Monte Carlo instead. Monte Carlo to the rescue. Monte Carlo pretty much always works. If I can solve for one set of resistors, I can solve for a million set of resistors. So here what I'm going to do is pick a random number for R1. R1 is 100 ohms nominally, somewhere between 95% and 105%. That's what this does. Picks a random number between 0.95 and 1.05. R2 is 200 ohms nominal, plus or minus 5%. R3 is 300 ohms, plus or minus 5%. Calculate the resistance of R2 in parallel with R3. Add that with R1. That's the total resistance. Calculate that, repeat 10,000 times. When I'm done, sort the data and plot the data versus probability. That's the CDF. What that looks like is this. Do that for 10,000 resistors. The resistance is somewhere between here and there. There's your CDF. Now, given the CDF, what is the PDF? Well, CDFs actually don't really do a whole lot for me. To me, all CDFs kind of look alike. So it starts at 0, goes to 1, kind of looks like a letter S. Is that a uniform, exponential? What's the PDF? Again, I'd rather have the PDF than the CDF personally. Well, in theory, I would just differentiate it. The problem is I don't know that function, so I don't really know how to take the derivative. If I do numerical differentiation, it's going to get really noisy. So what I could do is do a Monte Carlo for the PDF. That's a little bit trickier. What I'm going to do is have 2,000 bins. Each bin goes from 200 ohms on up, and I'll just count. The bin will be the net resistance. It's supposed to be 100. The net resistance relative to 200 ohms divided by 10. So every bin is 0.1 ohm. See how many times I wind up in each bin. I'll then count. Bin 1, bin 2, bin 3, meaning 200 ohms, 200.1, 200.2. When I'm done, plot the frequency versus the bin in ohms. And what that looks like is this. So there's the resulting PDF, starting from 200 ohms, going on up. A little bit noisy. That's probably when you take derivatives, you get noise. But that's kind of roughly what the PDF looks like, where each bin is 0.1 ohm, and you used a million resistors. What's the equation for that PDF? Well, I don't really know. This is where a Weibull distribution, a future lecture, is going to come into play. Given this function, I can curve fit it. Try to come up with a function to approximate it. That'll be a Weibull distribution. But this is one resistor in series, two resistors in parallel, what the net resistance is. And kind of note, every time I run this program, I get a slightly different answer. It kind of looks like a normal distribution. Trying to come up with an equation for that is something we'll look at a little bit later. But that's, again, one resistor in series, two in parallel. Another example. Suppose I have this transistor circuit. Each resistor has 5% tolerance. The transistor has a gain between 100 and 300. What is the voltage VCE? Now if we go to electronics, the equations are V Thevenin is R2 over R1 plus R2 times 12. R Thevenin is R2 in parallel with R1. The base current is V Thevenin minus 0.7 over R Thevenin plus 1 plus beta times RE. IC is beta IB. VCE is 12 minus RC IC minus RE times IB plus IC. And we'll just take that for granted. That you'll cover when you take electronics. For now, these are just equations that are a function of the resistances and beta. What is the resulting PDF for BCE? Well, again, I can use Monte Carlo. I can pick 10,000 random values for R1, R2, RC, RE, plus minus 5%. Beta is between 100 and 200. Once I have those values, find VB, RB, IB, IC, BCE, save them, sort the data, and plot it. So this is BCE. It's between 3.5 volts and 7 volts, looks like. Again, to me, all CDFs look alike. The PDF, at least for me, is more useful. To get the PDF, I could use Monte Carlo. I could, again, same thing, pick 1,000 bins. Each bin is 10 millivolts. BCE times 100. So the first bin is 10 millivolts, second bin is 20 millivolts, and so on. Once I find the voltage, count on each bin, repeat 1,000,000 times, and then plot the bin versus frequency. So that's what it looks like. So again, the bins are every 100th of a volt, every 10 millivolts. I've got 1,000,000 circuits. Every time I run it, I get a slightly different answer. It's a random process. But the shape kind of stays the same. That's the distribution for the voltage BCE with all these parameters. It kind of looks like a bell-shaped curve. So in summary, uniform distributions are fairly common and easy to model. It's the RAND function in MATLAB. That's a uniform distribution between 0 and 1. It is, well, one way to model the tolerance of a resistor, somewhere between 95% and 105% for 5% tolerance resistor. The gain of a transistor, again, the gain is somewhere between 100 and 300 for a 3904 transistor. Those are all uniform distributions. When I put resistors in series, they add. So what I'm really doing is I'm adding uniform distributions. When you sum uniform distributions, it very quickly converges to a bell-shaped curve. That's called a normal distribution. That's the central limit theorem, an upcoming lecture. To combine uniform distributions, you've got a couple choices. I could use convolution in MATLAB. I could use multiplication using Laplace transforms, i.e. moment-generating functions. I could integrate by hand, which is really painful. I wouldn't do it that way. Another approach is Monte Carlo. So when I add uniform distributions, I can use those approaches. When you're doing other combinations like inverses, resistors in series and parallel, various things like that, it's not quite as clear how you combine the distributions. In those cases, Monte Carlo simulations work really well. That's oftentimes what's used in circuit analysis. If I want to find out what is the variation in a circuit, I can use a Monte Carlo simulation and see what the PDF or CDF looks like. So that is lecture number 14 for random processes, uniform distributions.